I'll get started. Firstly, it's an honor to follow a talk with such a great mustache, with another mustache. But I'm Olshansky. I'm head of protocol at Grove. We're building out the decentralized pocket network protocol. And today, I'm going to be telling you about relay mining and decentralizing gateways. In order to help some of the concepts stick, what I really want to do is bring along a friend, Roni the Relay. I've decided to anthropomorphize a network request, and he'll kind of come and go throughout the conversation. Uh, but this journey has actually been going on for a little while. So 2 years ago, I presented the very first specification of the next version of the protocol. And last year, what I did is presented how we're framing the problem. And I'm going to reframe it today and go into more details. So what's on the agenda? I'm going to talk about RPC, talk about what we're actually trying to solve. I'm going to talk about relay mining, which is a paper that we published. And I'll focus on like how do we really incentivize query read-only requests. Then I'm going to talk about decentralizing gateways and frame and explain how we're thinking about this, because it's a really big problem in the industry as a whole. And then finish it off with some future work. So one of the things I really want to hammer in is if there are only two things you're going to leave this talk with, it's being able to answer how do we incentivize read-only requests? That's number one. And then number two is how do we delegate trust amongst multiple gateways? Those are the two things we really want to solve. And then what you're going to learn is that, even if you can get free lunch at Eat Denver, and it's going to be great, there's no such thing as free RPC. Okay, but before I get into the meat of it, why even listen to us? So I stand on the shoulders of giants. We have a big ecosystem. Some people have left, some people are here. We're always growing. And what we have done over the last few years is built, launched, and are continuously iterating on the first ever decentralized RPC protocol out there. And, aside from just talking about it, what are the numbers? Well, mainnet has been live for over 3 years. We've serviced more than 700 billion requests up until this point. And just last week, we managed a consensus-breaking release amongst our 1,000 validator network. So these are the numbers to back it up. And if you need any other reasons to listen to me, I'm already here on stage. You might as well just do it. Okay, RPC, they stand for three simple letters. It stands for remote procedure call. And the way I want to go about it is it's 3 letters, and we can break it down to 3 types of requests. There's a type of request that triggers compute on a remote server. There's a type of request that carries data, it carries a payload to a remote server. And then there's a type of request that carries data from a remote server. The first two, we usually think of as transactions. The last one is we usually think of as queries. And the big problem in the industry today is incentivizing that query, that read transaction. Right? Because even if we manage to incentivize and decentralize it, like how do you actually do this? And why do we need to do this? And the reason we need to do this is because blockchains were built for writes, right? When you think about it, it's all about sending data, having safety and liveness when you create a state transition amongst a decentralized set of nodes, right? This is what blockchains were designed for. This is what they were built for. This is why there's on-chain MEV. This is why there's MEV. This is why there's on-chain auctions, because it's all about writing data. But as developers, what we know is that the universe of write requests is much, much, much smaller than the universe of read requests. I'm sure that if anybody here has ever developed anything, the first thing you want to do is get an RPC node and start making some queries and getting data to build an application. And this is what RPC nodes were built for, right? And when we evaluate them, we think about it completely differently. We don't think about what's the time to finality. We think about what's the round trip time, what is the latency, right? You don't think about how many transactions per second it can handle. You think about, well, if I have a surge in traffic, can I still meet my SLAs? And for this reason, there's a very big ecosystem of RPC nodes out there. This is just a subset, but there's probably hundreds. And if you go on rpclist.com, you'll find many more. And the other thing is that when you want to evaluate any of them, what we did is came up with the RPC trilemma. You want every single node to be reliable, performant, and cost effective. But in order to really make it happen, what we've learned launching and building a decentralized RPC network is that you need both suppliers, which come from a network like POKT, and then you need gateways, which we're building out Grove to build a performance layer on top of that decentralized RPC network. So that's the problem. That's what we're actually trying to solve. And now the next few slides are going to get a little heavy, but stick with me because this is relay mining. This is really interesting. It shows how we actually prove on-chain the commitment to read-only requests. And to build some intuition, I'm sure a lot of people are familiar with Bitcoin and how there's Bitcoin mining. So the way relay mining works is that we start mining. You start handling requests. You handle requests, you handle another request, you handle another request, until eventually you find the golden Roni. And that's when you find the golden Roni, that's when you get paid. So all of you guys know how relay mining works now, and I'm pretty much done. Okay, no, I'm just kidding. Um, I want to build some intuition around this because there's on-chain actors and there's off-chain actors. The on-chain actors is there's an application, and the application stakes in order to prepay for services. There's a supplier, and the supplier stakes in order to advertise and offer services. And then there's a gateway that proxies them. And then clients actually send the relays, the RPC requests, that go through this whole network. The intuition that I really want to build is that in Web 2, we have token buckets and window and token-based bucketing algorithms to do rate limiting. I'm sure a lot of people here have gotten rate limited in the past, and it's all deterministic. Web 3 is a little different. In Web 3, we have optimistic rate limiting. So we create an incentive for you to service as many requests as possible, as quickly as possible, as efficiently as possible. But when that incentive goes away, you basically have no more incentive to service the application's requests. That's the intuition around all of relay mining. And the reason this is possible is twofold. It's because in Web 3, we have two things that Web 2 doesn't have. It's a distributed ledger, and it's something at stake. And we're using both. So relay mining at a glance is very simple. Step number one, we got to find Roni. We find Roni, we build the tree. Step number two, we have to prove Roni. So this is our claim and proof lifecycle. I'm going to talk about it, but it's find Roni, claim Roni, prove Roni. That is it. And even though it's that simple, there's a lot of cryptographic techniques and schemes that we use to make it happen. Most of these should be familiar to you, but the last three are actually where we customize it for our own specific needs. And I'm going to go into the details of why and how in a moment. The very first step of relay mining is handling a session. We have a formal explanation of how a session really works in our paper, and I do recommend that you go and read it, but I'm going to keep it very simple for today. Assume you have one application, one supplier that are paired together through on-chain data, and throughout a minute, the application is allowed to make 100 requests to the supplier. So one app, one supplier, 100 requests over 1 minute. This is basically something that the protocol gives you. And what relay mining does is the supplier is going to start handling requests. It's like, I'm handling requests, I'm handling requests, and then until it finds 100 golden Ronis that it can get paid for. Once you reach that limit, you're not going to get paid anymore. You no longer have an incentive to service any more requests, and at that point, you should just start rejecting it, right? Because we have a distributed ledger, and we have something at stake. Once a session ends, you found all your golden tickets, all your golden Ronis, you have requests, and you have responses with payloads. We take all that together, and this is where it gets a little technical. we have to put that together into a structure, right? We put that together into a structure, into a leaf. And the most important thing that I really want to call out here is that the request and its payload is signed by the application. The response and that its payload is signed by the supplier. Something that I really want to hammer in, it doesn't matter what the request and the response is, right? We can think blockchains, we can think AI inference, we can really think anything we want here, right? It extends beyond just an RPC query. And that's why we have the weight, the compute units, because different sort of requests may have different costs on the supplier to process. AI inference is expensive. Running a query against your Postgres DB is cheap. But we take all of that, we sum it up, we create a structure, we serialize it, we insert into the tree, and this is a sparse Merkle tree where every single leaf is a request-response pair. I'm not going to go into the details of how a sparse Merkle tree works, but we can talk about it later, or you can kind of read about it online. The key of the sparse Merkle tree, and this is why we have modified it to be a sparse Merkle sum trie, is that the commitment. We need to commit to the amount of work done throughout that entire session. It might be one relay, it might be 100, it might be a billion. But up until now, I've been talking about requests that we're handling, and I've been talking about these golden ronies they get paid for, but I didn't actually explain how you find them. What we found from experience, because at one point our network was handling 2 billion requests a day, is that we really need to scale, especially as we want to expand to other markets. So what we do, that structure, that leaf, we have an on-chain difficulty that gets modulated based on how much, based on the number of requests the network is handling. So if you think about it, that once we're handling 1 trillion requests on chain, we really need to modulate difficulty up so that the hash of the request response actually meets the difficulty, and every single supplier can handle a session with reasonable compute, with a reasonable amount of compute. So what this is going to do, it's going to scale beyond a billion, beyond a trillion. There's really no limit, but it gets modulated in the same way that other difficulties do. This is the claim and proof lifecycle that I'm going to go through quickly. It's a commit and reveal scheme, but the most important thing that I really want to show is that when we commit to that route where you say how much work you've done, we need to prove it later. So what happens is that we need to use on-chain entropy as a seed to figure out which branch we prove inside our tree. What this makes it do, it's completely non-interactive. The leaf contains the signatures for the application and the supplier to prove who was part of it. The root proves how much work was done, so we have validation across the entire stack. And there is one small nuance where you might be pointing to a subtree that's empty. So again, we modified the proof to have a closest proof, but we can talk about this offline because this can get really dense. Okay, that's really mining. I know that was a lot, but that is how you incentivize and prove read-only requests. And right now I want to talk about decentralizing gateways. So when you think about decentralizing gateways, it's all about delegating trust across multiple gateways. And what we do is we use ring signatures. And kind of what my friends told me is that rings are a great way to commit and delegate trust. But the only ring I still have to this day is the engineering ring I got from my university. So gateways versus suppliers. The delineation here is really important. It's because gateways, they're basically a gateway between a client and the suppliers. They help you proxy the request. They give you SLAs. They give you guarantees. They give you performance. They give you quality. But gateways can't operate without the backing supplier network, right? These are individuals that are experts at DevOps. They can fine tune everything to the minute detail to make it cost efficient and run as fast as possible. The important thing here is this extends far beyond just open source, far beyond just blockchain. It extends to all of open source. Because you can think any open source service can leverage this dichotomy between suppliers and gateways on top of them. And this slide right here is probably my favorite slide of the presentation, because what it shows is that we can have sovereign applications, which are your tornado caches of the world. They don't want to trust anyone. They keep their private key. They talk to the suppliers themselves. We can have a delegating application, which is basically, if you're sending someone $1, you can trust the gateway. If you're sending Olshansky.eth a million ETH, then you probably don't want to trust the gateway. Uh, and then there's a gateway application, which is basically how node operators work today. It's, all of the RPC, decentralized RPC stuff is abstracted out, and it's how Grove works today. It's like how Infra and others work today. It's very Web 2. But all these three systems and approaches are not mutually exclusive in the system we're building. So it's up to the client to figure out what they really want to do. How this works at a technical level, I'm going to go through it quickly. So it's 2 steps. Don't blink. Actually, maybe you should blink. Number 1, we have a distributed ledger. So with my application private key, I say, I trust this gateway's public key and send it on chain. That's it. I just sign a request and trust it. Number 2, when we sign a request, what we do is instead of signing with the application's private key, we create a ring signature with all of the public keys. So it doesn't actually matter who signed it. It's the application that pays for it, but whether it's Gateway 1, Gateway 2, or the application that signed it, it does not matter. And what this enables is this beautiful world of gateways, suppliers, leveraging each other, focusing and harnessing their superpowers on product or infrastructure, and having a balance between the two. So in terms of future work and collaborations, there's what I presented is what we're focusing on. It's what it's what our superpowers are. It's what we're really innovating on. But we have tons and tons of ideas. Lots of things where it's either at the discussion stage or the design doc stage or the Telegram group message stage. So lots of things happening here. If anything here interests you or you're thinking about it or you're designing for it, really come up to myself or someone else at Grove or at Pocket, kind of tell us what your project is doing, and I would love to find ways to collaborate and work together. I'm Olshansky, and thanks for listening to my talk.
Awesome talk, Daniel. I'm down for the WebSocket support and that you mentioned on the last slide. Can you walk us through the what exactly is a supplier in this architecture diagram? Because also, I don't understand RPC so well, because you have a read that just wants current state of the blockchain, and then you have what might also run some logic, I don't know, and then you have writes which definitely run logic, and then what does the gateway do there?
So your question is like, what is a supplier in the entire in the end-to-end process?
I guess.
Yeah. So okay, right here in this diagram, we have a client, right? So a client is your iPhone or your browser, the one that's actually the user that's originating the request, right? Completely off-chain. The gateway is an on-chain actor that can proxy requests on behalf of an application or a client. So right here, you see the suppliers on the left-hand side, under which we have being supported by the Pocket network, decentralized kind of network. A client could theoretically talk directly to the suppliers, right? This is not easy. Like, how many people here in the audience run their own full node? All right, this is actually, it's pretty good. Like we got a good like 15%, 10 to 15%. But it's less than 80. Uh, right? So if you're using Tornado Cash and you're very sensitive about your application, you're probably a client that's going to want to talk straight to a supplier, or you're going to be running your own node. But if, for example, you're a business, or you can't manage your own node, or you don't want to manage the quality of service yourself, or you just want you want dashboards and API keys and everything that comes with a real product, everything that a centralized RPC provider gives you, that's what gateways are. So one of the things that we're actually doing with the next version of the protocol is aiming to make gateways completely permissionless. So anyone can come in and build a business on top of this decentralized set of providers without needing to run your own infrastructure. Just kind of focus on the features, like, data indexing, data validation, user auth, everything that comes with it. Did that answer your question, Derek? Thank you.
Any additional questions? If not, please give Daniel a big round of applause.